So hello and welcome to Living with Garbage. Today we're going to talk about garbage collection and its implication on application design and distributed systems design. So first a little bit about myself. So I work at Etsy.com right now, and before that I spent about 3 years working on Solr and Lucene at a job site called The Ladders. I want to talk about, this is an instructional talk. We're going to talk about enough about garbage collection theory to sort of give you a useful mental model of how garbage collection works. We're going to talk about how to monitor garbage collection and how to design your applications to be resilient when garbage collection pauses happen. And it's not going to be an incredibly detailed walkthrough of every flag and every possible JVM collector. A lot of that stuff is available online, and I'll point you to resources for that stuff. But it's sort of the stuff around that, how to design applications, how to monitor them, system level things that you have to keep in mind. So it's sort of a practitioner's guide and based on our experiences at Etsy. So let me tell you a little bit about Etsy. Etsy is an online marketplace for handmade goods, vintage goods, and craft supplies. And most items are handmade and made by a large community of sellers from more than 150 different countries. And we connect shoppers and independent creators and designers to find inspiring handmade goods and providing artists and creators a platform on which they can build their own businesses. So many of these sellers make a living selling their goods on Etsy. And the site has more than 8 million members, more than 20 million different items, over 800,000 active sellers, and we get more than 8 billion page views per month, putting us in the top 50 in the U.S. And it's a pretty unique site. Lots of interesting items, lots of very talented and creative sellers. Here's a few of my favorites. These are little statistical distribution pillows, and if you can name all 6 of these distributions, I should remind you that we're hiring data scientists. So come talk to me afterwards. Even if you can only name like 3 of them, still come talk to me afterwards about data science. Here's some more of my favorites. Crocheted Conan. This one we have on the wall at Etsy. It's that kind of place. And because we're in San Diego, right, these guys. I was tempted to put lots more of these in. So it's a very unique marketplace. It's very different than other e-commerce sites in that items come into the marketplace and then go out of the marketplace very quickly. If you make a one-of-a-kind handmade sweater and you list it, by the time we've got enough data to really know how to rank it and how to recommend it, somebody buys it and then it's gone. So it presents very different challenges than Amazon or eBay or sort of bulk marketplaces. And even in terms of building tools for sellers, sellers are usually individuals and may not be incredibly computer savvy. So we have to keep that in mind when building things like advertising platforms. You can't have people doing keyword arbitrage and things like that. It presents some new challenges. So we're in Brooklyn. We have about 450 people, and last time I checked, we have about 140 engineers. These are 72 of them. It's a pretty great engineering organization. Lots of folks who've come over from Google, Flickr, Yahoo, Microsoft. Very pragmatic engineering culture. Continuous deployment is a big focus. Monitoring, metrics collection is a big focus. It's very, you arrive as an engineer and you become very ops oriented as you go in your time there. So these are actually screen printed by our VP of engineering. We have a blog, an engineering blog I encourage you to read, and that's the T-shirt I'm wearing. We've actually got a few T-shirts to give away, so there'll be questions during the talk. So keep alive and you might win a T-shirt. So we talk about lots of different things about our infrastructure, MySQL, web performance, internationalization. It's an international marketplace, so that presents some interesting challenges. We do cross-language retrieval, which is something we should talk about here at some point, not today. So on the blog is some search-related things. We've talked about our BitTorrent replication, which is pretty unique. We use BitTorrent to ship indexes around our cluster. And we've got some highlights on there about our relevance tuning tools, a lot of custom-built relevance tuning tools. And we're pretty transparent on the blog about both successes and failures, which you don't always see. So we're going to talk about garbage collection and its impact on application design. And it's a very big topic. We'll focus on 4 major areas today with some coverage of some minor topics if time allows. So understanding GC, we're going to try to develop a sort of a working mental model of how the GC works and what are the challenges there, how to monitor GC, how to know what's actually going on, how to debug common memory leaks in Solr applications. Just because we're using garbage collected language doesn't mean you can't have memory leaks, and we've had a few of them, big ones. And how to design for partial availability. If you're going to have garbage collection pauses, how do you acknowledge that and account for it in your system design? So I often find when you start on working with garbage collection, I sort of found myself sort of monkeying around with the different JVM parameters, not really having a great idea of what was going on under the covers, and very quickly, setting CMS initiating occupancy frequency and things like that, and not really having a great idea of how it should work underneath. So it's sort of a black box at first. So let's start with a very simple piece of code, and we'll walk through it, and then we're going to try to pretend that we are the VM, and we're going to stop the world and garbage collect, and let's talk about how it might work. So we have our buzzword detector, and we've got some static prefixes, so some static terms, and we're going to walk through. We've got some arguments there, and so let's go through it line by line. So it's main, and we go through the args. We lowercase them, so that causes another string, and we walk through, and if the lowercase version of the args matches one of these prefixes, we print out the buzzword count we found in our list. So let's think about this in terms of allocation and garbage collection. So as we walk through, what objects do we have? Well, as the class is being initialized, the statics are put on the heap, and references to those statics are added to the class level static data. The args array is allocated, and a reference to it goes on this thread's stack. As we loop through, to lowercase internally allocate some objects, and creating a lowercase version of the string allocates another object that goes onto the heap, and that reference goes onto our thread stack. And so let's say we go through this loop. We go through this loop once. We go through this loop twice. And at the end of our second loop, we run out of heap. So the heap is full, and we get to this point after doing 2 loops. So we're in our third loop, and we have to allocate another object, but the heap is full. So let's talk about how allocation actually works. So when allocation works, and this is a pretty simple model of it, and this is from a book called the Garbage Collection Handbook, which I recommend, and there's more about later. So when you go to new an object, it'll try to allocate it, and if that doesn't work, this is sort of a pseudocode of how it works. If that doesn't work, it'll call the collector, and after running a collection, we'll try to allocate again. And if that doesn't work, that means the heap is still full, and we haven't been able to collect anything, and so we'll have to. It's an error. We're out of memory. And so here's collect. So this is a simple mark and sweep garbage collection algorithm, and so. The JVM collectors don't use a basic mark and sweep algorithm. They use mark compact, mark and copy. But this is a useful model of how it works. So how does collect work, and what does mark from roots mean? So basically, mark and sweep means we want to find the roots. So if we have a graph or tree of references, we want to find the roots of that tree and traverse them as we're doing here, and mark each thing as live. So we want to find some live objects, the roots of our live objects, and traverse from there and mark each one of those as live. And then when we get to the end, we know that everything else is garbage, and it can go away. And so that's basically how the marking works. And so if we go back to our trivial example here, So after we've gone through 2 loops of this, and we try to lowercase a string, and we need to allocate more memory, let's think about which objects are on the heap and which objects might be garbage at this point. And so what are our roots? So can anybody give me, so we've done 2 loops of this, 2 loops here. What are some of our root objects? Anybody got a root for me? What's that? The thread stacks are a root. So every live thread, the thread stack, and you're going to walk the stack to find live references and statics. Yep, absolutely. The statics, and then things like registers. But basically, the big thing we're dealing with here is the statics, are the statics, and our main, the thread that's executing our main. And so after we've done 2 loops, we can go through and we start with the statics. Actually, let's take it back. Let's say we've just done 1 loop. We've done 1 loop, and we go through, and we need to allocate. And so we have, when we walk the tree, we go from prefix, we see those objects. We go from myargs, we see these objects. The object that args originally referred to, though, no longer has any references. So that can be collected. And the objects that were allocated within here end up not getting marked at all. So the things that get marked are these statics. And so let's say we get down to contains after another loop, and contains wants to allocate some memory in there. The subsequent object we've allocated into lowercase now has nothing referring to it, but the lowercase within the current loop does. And so that's basically how the marking and sweeping goes. And each time, the objects that are not referenced can be collected. So a quick bit of trivia. So who invented the first mark and sweep algorithm? That's right. Yeah, John McCarthy in 1960 invented mark and sweep as part of Lisp. And so one thing we may have noticed, going back to our example, is each time we go through this with our sort of simple mark and sweep algorithm, we're starting from those statics and walking their references every single time. So as we go through this loop, if we're garbage collecting and we start with the statics, those statics have to be traversed and marked every single time. And so there's some real loss of efficiency there. And so that leads into something called the weak generational hypothesis, which is that some objects live a very short time and some objects live a long time. And in most programs, not every program, but in most programs, you'll have very short-lived objects, and you'll have things, caches and statics that'll sit around for the life of an application or a very long time. And so you can think about these things in the context of a common Solr application, and where these objects will how long these things live. So the things at the Solr request level will tend to live a very short time, whereas something that's in the tree pointed to by an atomic reader context or a Solr index searcher will last a very, very different amount of time. And sometimes these, depending on how often you update your index, Solr index searchers might update every minute or every 20 minutes or every day. And segments will last until they get merged out or no longer referenced. So those could last quite a long time. What modern GCs tend to do is to separate out short-lived objects and long-lived objects. So when you hear about this in context of JVM, there's the new generation and the old generation. And the new generation is where every object starts out, unless there's not room in the new generation. But generally, every object starts in the new generation, and it tries to be collected and tries to be collected. And after a certain number of times, if it can't be collected, it gets tenured out. So it ages out into the old generation. And so that's so there's a bit of terminology before we go into the different JVM collectors that's worth going into, and can be a little bit confusing. Concurrent versus parallel in the context of garbage collection. Concurrent means the garbage collector tries to do some of this work while your application is live. So we described a situation where the application was completely stopped, and we got to do our mark and sweep while the application was stopped. But if the application was still running while we were trying to do that, it's a much harder problem. When we talk about a concurrent collector, we talk about a collector that is trying to do some portion of the work while the application is running. And that's a harder thing to do. But then parallel really means parallelizing that work among multiple cores. And so the JVM collectors, there are four main collectors in the Sun JVM, and then one commercial one that's worth talking about. The serial collector, so the space in the new generation is collected with a single-threaded stop the world copy collector. And so when a collector is a copy collector, it is marking the objects and then moving the live objects to a new space. So all the live objects get moved to a new home, and then that old space is just full of dead objects or open space. And so you can just completely collect that old space, and you know that the space where those things have been copied to is just full of live objects. So that's the basics of a copy collector. So in the serial collector, everything is single-threaded, including collecting the old generations, also single-threaded. And because there's no space to copy to in the old generation, it compacts as it goes. So that's sort of the trade-off in GC is either you are spending a little bit more, having extra room, having basically twice as much room as you need and copying, or you're compacting and trying to minimize the space. So when you think about copying, when you think about the VM is actually copying and moving your objects around, it brings up a question. So I always thought that system.identity hashcode was, and I don't know if you've used this, if you use an identity hash map, you're using this underneath. How does system.identity hashcode work? I thought it was based on a memory address of the object, and that's how it was always the same. And so what it actually does is it's based on a hash that happens once, and then that gets copied to the object's header. So if you look at a 32-bit object, 25 of the bits are the hash that system.identity code records the first time. Then the object can be moved at will, and you'll still get the same identity hash code. So that's how that works. I'll go through this kind of quickly. So throughput is very similar to serial, except it's parallelized. The old generation is parallelized. The new generation is parallelized. CMS is the low pause collector. So it's the concurrent low pause collector. So basically, we're trying to do as much work as we can in parallel to the operation of the JVM. Due to the design of it, sometimes it has to fall back on stop the world collection, and the throughput is less than you have in the throughput collector. And so sometimes you can not be able to catch up. So sometimes with CMS, we've hit a wall where allocation rate is high, and it's not able to get enough work done in concurrently to the application running, and it'll hit a wall and basically just spend all of its time GCing. And this requires a lot more tuning, whereas throughput can self-tune. And so the successor to CMS, due to its limitations, is something called the garbage first collector, or G1 collector. And this is the newest collector in the Sun/Oracle JVM. This has multiple spaces, and it tries to concurrently figure out which space has the most garbage in it, and then collect that. And so that is the newest one. The commercial collector of interest is called C4. It's by a company called Azul Systems, and it does concurrent collection both of the new generation and old generation, and has amazingly low pause times. If you look at some articles, like Mike McCandless had an article about testing Azul with giant 100 gig heaps and seeing 10 millisecond pause times. It's pretty amazing. So other JVMs I don't know a ton about, how those work. IBM Dalvik, I can't really dive into how those work. There's a decent amount of freedom for implementing these things. So why does Etsy use throughput, at least right now? For us, it's required the least amount of tuning, and it's been most amenable to changes in load. So if there's a spike in traffic or the workload changes over time, we've been better able to handle it. Whereas with CMS, it's been more brittle. But you do have pauses. You have an old generation that takes a long time to collect, and so if you hit an old generation collection, you'll see a pause, sometimes a multi-second pause. But the pauses for us have been predictable, and the VM recovers. Whereas with CMS, sometimes we've just not recovered, and we've basically had to restart machines. Okay, any questions so far? Oh, I'm sorry. Have we done any comparison of, and I have a mic. Have we done any comparison of G1 and throughput? We started to, we tested G1 in 2011, 2012, and it crashed on us repeatedly. So it's, and I've heard this from a lot of people, but it's been a couple of years. We intend to try it again soon, and I know some people have good results with it, and people use it in production, but we didn't have good results when we tried it. It looks intriguing. It looks like it could be really good. I guess predictable is probably the wrong word. The question was, you said that the throughput collector was predictable. What does that mean? And predictable is probably the wrong word. The pauses themselves are reasonably predictable in that they happen every so often if your application has a constant allocation rate, and you're updating your index every 10 minutes, and things go into the old generation, and you can sort of watch it over a long period of time, and you have a good idea of when these old generation pauses will happen. But I guess resilient is probably a better word, in that we know it's never going to just kind of go away and be overwhelmed by allocation. It might pause for 3 seconds, but when it comes back up, the old generation will have been collected, the new generation will have been collected, and it will resume doing useful work. Whereas with CMS, we'll sometimes hit a very, very abrupt wall where GC time will go from 3% of application time to 98% of application time, and it'll just stay at 98. And we just have to start it over. They both use multiple cores. CMS is trying to get work done while your application is running. So it's trying to be clever and in the background while you're allocating, mark which objects are still live, and then try to do things that require stopping the world, like moving objects and compacting, trying to do those with as small a pause as possible. And it's got all sorts of tuning parameters and ergonomics that sometimes worked amazingly well for us, but then when they would fail really badly. Okay, cool. And I'll take questions a couple more times as we go. So I'll talk about the exciting problem of monitoring garbage collection. So how do we know if garbage collection is even a problem for our application? And what's a reasonable amount of time to spend garbage collecting? So I'd say for the latter question, what's a reasonable amount of time? If you're spending more than 3 to 5% of your application's runtime in garbage collection, depending on the collector you're using, it's probably not working as well as it could be. But if the collection is happening at a time that doesn't influence user requests, then it's really not a huge deal. So one thing we can do, one thing we've done, is to measure the GC time per Solr request. So basically figure out how much time during, let's say you have a 1 second Solr, a 2 second Solr request, how much of that time is actually figuring out what the results are, and how much of it is pausing the VM and doing garbage collection or other types of pausing. So we've done this by basically at the beginning of a request and at the end of a request using the JMX hooks to get the total collection time that has happened so far, and just taking the difference at the beginning and end of a request, and then logging that and using that in analytics to try to figure out how big of a problem we have at any given time. And this has prevented us, before we had this, we would see slow queries in the logs and start debugging why the query was slow. Why did this query take 4 seconds? But now we're able to subtract the garbage collection time to figure out what's actual Solr time and what's actually just the VM cleaning up. So this was very useful. So when I do see we have a problem with garbage collection, the first thing I like to do is to look at the heap. I find it's very useful to get a visual picture of what the heap is doing, where the memory is, and so for that we use something called VisualGC. And here's a picture of our heap from one of our servers from a few minutes ago. And so you can see the weak generational hypothesis at work. Here's a throughput collector. Here's the Eden space where new objects are allocated. Here's the old space where objects are tenured out to. And then sort of this is the different survivor spaces. So an object is not just tried to be collected once and then put immediately into the old generation. There are different ways of tuning how many times you can try to collect an object before you declare it old, because it gets much more expensive once you put it in old. So you want to be careful about it. But it's a balance. You don't want to be too careful. You don't want to try 500 times before you put it in the old generation, because then you're wasting time too. And so it goes up to 15 different times you can try, and you can't set it to more than 15 because it's only 4 bits in the object header, I believe. So that's why it's the maximum is 15. And so VisualGC will also show you total number of collections, total amount of collection time, graphs of the Eden space, graphs of the survivor spaces, graphs of old generation. So it's very useful to get sort of a first look at what's going on in your heap. And it's kind of fun to sort of watch it go up and down and watch the Eden space go up and then get collected and watch it go up. It's hypnotizing. On a slow day, I guess it's hypnotizing. So you look at the heap, you see you've got some sort of problem. Things are pausing way too long. It's not working efficiently. Your request level Solr monitoring shows 15% of your time is spent on garbage collection. So how do you get more information about what's happening? So there's all this logging you can put into the VM. There are a million different parameters to tell the VM to print out all sorts of very useful stuff to a log. This is what we have. There are other parameters. By default, the VM will tell you just a time from when it started to right now, and that's not very useful if you want to correlate it with other events. It just takes a lot more work. So you can actually have it print out date stamps. You can print out a summary of the heap, which we'll see in the next slide. It'll actually show you how many bits, the memory addresses. You can tell you the application stop time. So application stop time is not always just garbage collection. So that's one of the things that the VM will stop for. It's usually the biggest, but there are other what are called safe points in the VM where the VM will need to bring threads to a stop and do some work, like maybe de-optimizing a stack frame or something like that. And this can actually take a decent amount of time because not every instruction in the VM is a safe stopping point. So if you have a tight loop with no method exits that's doing a lot of math, that might run for several seconds before it hits a safe point and the VM can stop it. So if you print out this application stop time, you can then get a full log of all those different times and you can graph them. Adaptive size policy prints out, if you have adaptive sizing on, where you let the VM figure out how big Eden space, how big the survivor spaces should be, how many survivor spaces you should have. So keep statistics on your allocation and the expense of your collections. And so you can have the VM print out all the statistics about the size policy and how often. This means every single time. Tenuring distribution will give you how many objects are in each survivor space. And then safe point statistics will give you more information about what's happening at those safe points. So you can see lock lesion and things like that happening. Then you point it to a log. This log, unfortunately, is you can't format it with like log4j or your logger. It happens at too low of a level, unfortunately. So what does this give you? So this is an actual log we're going to see from a machine. We were testing a new Solr feature. And I think I don't really need to tell you what's happening here. It's pretty obvious. But I guess, can anyone actually even read it? Probably not. All right. But so this is what you get. You get a big barfing of information about your heap. And then you've got to make some sense of it. But this is a time where we basically didn't have enough RAM for putting the R index into memory. And and you see at the end of a garbage collection, our even space is still 93% full, so the new objects didn't even get collected, and the old generation is 99% full, so nothing is getting collected. So we're at the end of a very expensive collection where you see it took 8.7 seconds in real time, and in user time, 137 seconds, so we did get some parallelization. But we get to the end, and we still have tons of garbage, so we're hosed here. So how can you make some better use of this information? So it'd be nice to have a log analyzer that worked really well and just pulled out very useful information from here. And I've tried a few of them, and it's kind of slim pickings. GC Histo was recommended, but it seems to be unmaintained. GC Viewer, I've had to patch to get anything useful out of it. Garbage Cat seems to be the most up-to-date and maintained, but I actually could never get it to read our logs. So if somebody can get one of these going with that sample that I have up there, that would be much appreciated. So what we do is we manually parse these things and just take the information we want out. So we have this logging framework called Logster, where you write a little Python class and basically spit metrics out. So you just parse line at a time and spit out the metrics you want, and you can send things to Ganglia. And so here's an example of one of our Ganglia graphs of the GC stop time. So here's some of our slaves and their stop time. Ganglia for fractional things is a little bit confusing, but these graphs are incredibly useful, and the spikes usually correlate for us with a new searcher. So we've got a new segment, we've got a new searcher. There's a bit of a spike, and so eventually you'll have tons of these graphs, and so you want some sort of dashboard where you can see everything together. So we have a dashboard framework. And you can aggregate metrics from all over the place. Graphite, Ganglia, Cacti, New Relic, plug in your own, contribute it back. It's open source. So here's an example of what it looks like. So you can sort of slice and dice by time range. And the vertical lines are sort of the most useful thing we do. And then you can see different events. Like somebody did a configuration deployment here. Somebody deployed the website here. And then you can see things like the JVM stopped right there. So when you see big spikes, when you see things happening, you can correlate them with external events. So this is open source, and you can build these dashboards pretty easily. It takes very little code to build a very sophisticated looking dashboard that it looks like you did a lot of work to build. So if we're actually looking at the heap itself, I love YourKit. They're open source tools. I like YourKit. It's been done very well for me. But one tip is to not leave the agent running in production on every machine accidentally, because that will affect your GC pause time. So it's a very low profile monitoring agent, but not low profile enough. So I would just leave it on when you're really testing things, and then don't have the code weaving happening. So I think you do enough monitoring and you do enough GC tuning, and you get to the point where you realize that you're never going to make the pauses go away. You can try, and then there's always going to be pauses. There's always going to be, or maybe you're deploying, or maybe you're just under a tremendous amount of load, and you just can't. You get to the point where you realize that just because you're sending a query to a server doesn't mean you're actually going to get a response back from that server. And so the first thing we tried to tackle with this is just not sending so if we have these big pauses, how can we just not send a query to a machine that's actively garbage collecting right at that second? So it feels like this is something we should be able to, if we just avoid that, if we have these not predictable but resilient pauses that last for 4 or 5 seconds, and they happen every so often, we just want to not send queries to a server during that time. So how can we do that? So the first thing we looked at is the JVM-TI, the Java Virtual Machine, something with a T interface. And basically, you can write a C extension and get different events. So you get garbage collection starting, garbage collection ending, and you can do whatever you want. So we thought it would be very clever to just shut down the network interface at that time. So if garbage collection is starting, we just shut it down. We just make an IP tables rule and stop accepting new traffic. And that worked. And then when the garbage collection is over, we bring it back up. So we thought we were very clever, and it worked pretty well. The problem is that the pauses we care about are these giant pauses, but the pauses that overwhelm them are really very small. You get 10 millisecond pauses to do a full stop collection on the new generation, and it takes 50 milliseconds to shut down your network traffic. So you get the network is going down, 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 down. So it ended up being a big headache. So still, how can we ignore when a server is garbage collecting? We don't have that solved. And at one point we had a couple of memory leaks, which we didn't realize at the time, but we had these giant pauses that would go on and on and on, and sometimes we'd have half of our cluster doing outrageous garbage collection. And so if you sent a query at that time, you had a 50-50 shot of just never getting a response back. But there were these other 50% of servers who would happily accept your request. How do you send it to them? How can we ignore the hosts that are GCing? So one thing we have to keep in mind is that the server will lie to you about its availability. You will be able to make a TCP connection to a machine where the VM is garbage collecting for 10 seconds. You'll be able to send some bytes to it. There's a TCP socket receive buffer. There's a TCP write buffer. So the OS is just lying to you and lying to you again. You connect, you send it a query, you think everything's going well, and then you wait and you wait and you wait and you don't get anything back. So because the VM is pausing. So what we want to do is some way to just see, we just want to know, can it execute Java code right now? And so what we do is we have something called the banner protocol, an invention of ours. So we do make a TCP connection, and then we wait somewhere between 1 and 10 milliseconds. We've tried different tunings. And we have a magic 4-byte header that the server sends us. And unless we get that header, we just move on to another node. So imagine a situation where half your cluster is GCing horribly, and they're never going to respond to you, even though they'll accept your TCP connections and accept your queries. Or they'll accept them up until you get to the OS's buffer limits. So in this case, we found very quickly, a millisecond or 10 milliseconds per GCing server is all we wait. And we just quickly find the ones that are still capable of serving queries. And only when we get those 4 bytes do we actually send them a query. So this worked remarkably even when we had half our cluster GCing, had almost no impact on latency and errors, and it was great for us. And the fun part is that the 4 bytes. So this is as close as I could get to our blog slogan of "Code is craft" in hex. So these are our magic 4 bytes. So that worked pretty well. We even made stickers of the 4 bytes. We were so happy about it. But then we realized, what if you're in the middle of a request and GC happens? So it worked pretty well to avoid machines that were GCing when you sent a query. So you didn't get a machine that was GCing at that second, but let's say you have a big 4-second query you're going to do, and 3.99 seconds into processing your query, the machine hits a giant garbage collection. You're never going to hear from it again. You're going to time out. You're going to get an error. So we haven't totally solved the problem, the availability problem. So we worked on next something called backup requests. So in this case, we're going to send a request to that machine. We're going to wait a predefined timeout, and then we're going to send it to somebody else. We're not going to cancel that request. We're going to send a copy of that request. And then whoever comes back to us first, we're going to use that result, and then we're just going to discard the other one. And this was inspired by a paper by Jeff Dean at Google called Achieving Rapid Response Time in Large Online Services that I highly, highly recommend you reading. I also highly recommend you reading anything by Jeff Dean. He's like the closed source Doug Cutting. He's pretty impressive. MapReduce, Bigtable, Google Search. And so this has worked really well for us. You could GC in the middle of that request, but after say 100 milliseconds, we've already of waiting for you, we've already sent a copy to another server. Now, what we haven't done is add a sophisticated layer of cancellation, and Google has something more sophisticated where they'll send that backup request and they'll wait for after say 100 milliseconds. Whoever comes back first, they'll actively cancel the other server, so the other server stops processing it, and that saves capacity. We don't have that yet, but that would be a great thing to have at some point. I think you need more sophisticated ways of tagging queries, and So this actually becomes an issue as we look at sharding. So at this point, we haven't sharded any of our indexes, and so it's actually something we're working on now. And we want to do very heavy sharding. We want to make very small shards, as I'll talk about later. And so let's say you shard an index into 30 parts, and you want to get results back from a replica for every single shard. You're bound by the slowest shard. And in this case, GC could be a limiter. You could be waiting for the largest GC pause on the last replica. Now you can do some timeouts on there and say, I only want to wait a second, no matter how long each replica takes. But then you lose some of your results. So it's not a perfect solution. So we would love to bring backup requests to Solr distributed search. So I think that's something we're going to be hopefully working on this year, is trying to add that in. Because what we want to do is this is a quote from the Jeff Dean paper, is make a reliable whole out of unreliable parts. So you could have unreliable servers, you could have people running things on that server, things could go down, but you still want the whole to be reliable. So let's talk about memory leaks, and then we'll take more questions. So memory leaks. So I mentioned we had some memory leaks at certain times in the past. So we write a lot of custom code. We have very specific needs, and especially in terms of relevance and indexing. So we use a lot of the custom Solr hooks that you might know about: queue parsers, request handlers, custom caches, custom search components, event listeners, value source parsers, custom queries. And so we've used all of these. And this is, if you're writing a Solr application, this is probably where the memory leak is going to be. It's probably going to be. It's not going to be in Solr code that's already in there. It's most likely going to be in something you wrote yourself, or at least it was for us. So one thing I should say, a little public service announcement, is if you're doing this, if you're writing custom code, really make sure you need it. Read the, because we've written custom code we totally didn't need, that duplicated stuff that was already there more times than I want to admit to. So read the documents, read the code, read Solr in action, read the Solr cookbook. And then most importantly, ask Solr user. And I use Solr user a lot of times to sort of, people talk about rubber ducking, where they describe their problem to a rubber duck, and that helps them solve the problem. So I do this with Solr user. I'll start typing up an email, and 1 out of 20 times I'll actually need to send it. Most of the time it just sort of occurs to me from going through that. So here's the two gotchas. Send it anyway? Okay. Okay. 14 out of 15 are pretty dumb, though. So it'd be kind of embarrassing most of the time. I'll send them under an alias. So here are the two big gotchas in terms of creating your own memory leaks. And you can go out today and create your own memory leaks all day long by using these two things. So when you get a Solr index searcher, certain points in the Solr code base, it's going to be ref counted. So it's doing manual reference counting. And reference counting is actually one of the ways you can implement a garbage collected system. You can count references as they're being, as references are being changed throughout the system. The VM can count references for you. So it has all sorts of problems like cyclic structures, and most serious VMs don't work this way. But Solr has some manual reference counting for very good reasons that I don't have time to go into. But there's manual reference counting. So just make sure when you're using a ref-counted Solr index searcher that you use it in a try finally, and in the finally you are decrementing it. You're releasing it. And it's a little more insidious with core container.get core, but you have to do the same thing. You have to close the core when you're done with it. It doesn't explicitly say it's ref-counted, but you have to close it. And we've not closed it and had cores lingering. So when we've had these problems, we've used a technique. So I like, as I said, I love YourKit, and a technique that I use to find these memory leaks is marking generations in allocation using triggers. So I can show you what that means. Basically, on events, it is an object as basically incrementing counter, a generational counter. And so each object it belongs to a certain generation. And when a certain event happens, it increments that counter. And so if your index is being updated every minute, and on minute 60 you see a Solr index searcher from minute 4, you probably have a memory leak. It shouldn't be around that long. You might have 2 Solr index searchers, or a couple of them if it takes a long time to warm up. You might have a few of them concurrently operating, but they should be within a generation or two. It shouldn't be 60 generations or 5 generations. And so YourKit triggers were very, very useful for this. You can basically hook into any method and apply different events. You can capture snapshots. You can advance object generations. And so for us, that worked incredibly well for finding memory leaks. And our GC problems were much harder because we had memory leaks and didn't realize it. So we learned a lot more about garbage collection than we actually needed to because we had memory leaks. So if you have horrible GC, it might be the first thing to look at is you just have a leak in some custom code. All right, so we'll take more questions. Okay. So on the first question, the first question was if you're planning to shard, you have a very large heap, and actually that was our QA cluster. So we have a 12 gig heap in our QA cluster. In production, we have 31 gig heaps. So if you're planning to shard, how big are your heaps going to be? And once you shard, we still have this banner protocol. We're still going to be worried enough about garbage collection, have this custom protocol to avoid talking to GCing nodes. So on the former question about what size I would say I have a section at the end, sort of forward-looking, more opinionated section about where I think we're going, and it's certainly not 31 gig heaps. So I'll get to that in just a few minutes. And as far as the banner protocol, I'm not sure. It's kind of an open question. We have an active email thread on our mailing list about should we have this custom protocol? Do we need it? And I'm not really sure. My hope of hopes is that Oracle just buys Azul, and there's never any bigger than 10 millisecond pauses to worry about, and then we can just delete it. It would be great. Anybody ever read The Difference Between God and Larry Ellison? No, it's a great book, and it's got this anecdote about Larry Ellison going to a house in the middle of the night, and the house was worth like $3 million. And he just walks I might be getting this slightly wrong, but he walks in with a briefcase with like $6 million, and he says he wants to buy the house, and the guy says, okay, oh great, it wasn't for sale, but okay. And then he says, okay, like now, and so he's like, guy puts on his bathrobe and leaves, and Larry Ellison just walks into the house right then. So I have these daydreams of him walking to the Azul offices when I'm busy debugging garbage collections with a big briefcase full of cash. Just buy it. Just put it in the JVM. We don't have Java 8. Give us something. All right. It is an easier solution. That's one of the things we're discussing doing. So the question was, rather than doing this complex banner custom TCP protocol, did you think about just putting a load balancer with an acceptable read timeout in front of things? And we did. We actually we run a bit of a custom stack at the moment. We have a Thrift interface. We have a PHP web front end. Then we have then we have our Solr servers, but we actually have a custom Java code that does query generation, and we talk between PHP and then we talk to an embedded Solr server. So we talk between PHP and our custom search servers over Thrift. And so we already have this kind of low-level TCP interface, and we don't know, we didn't think we had any sort of load balancing solution that would work at that level. And we do a lot of client-side load balancing. The other thing we do, and we may keep this or may not keep this, is we do query-based affinity. So we hash a query and prefer a particular node based on the contents of the query to try to increase our hit ratios. And if it's not there, we go to another one. It's sort of but that's another thing with a load balancer we would lose out on. But that solution might be something we revisit, especially in combination with backup requests.
Quite interesting. Going on
The most recent Solr thing. Sorry, are there any other events in Solr that like we were doing with YourKit, triggers on new searchers that would be useful to hook into that have a big effect on GC? We really found it's Solr Index searchers coming and going that because you get all the caches get recycled, so the caches have to be sort of rebuilt, and that's lots of allocation happens there. And if you have new segments coming online, so you have all of the data structures around a segment, so that might age out into old generation over a course of a few collections. So those tend to be the heaviest things. The heaviest GC thing I'll talk about towards the end, which is basically putting all of your postings in RAM. And so I'll get to that at the end. So I'll take more questions at the end because I think we're getting reasonably low on time. So let me blow through some miscellaneous topics. When should you call system GC? The received wisdom is you should never call system GC, and for a while we even had disable explicit GC in our configuration. So now we have it in one place, which is when the server starts up, we let every index searcher for every core warm up, and at the last second before we turn on our server sockets to accept TCP connections, we do a big system GC and clean everything out. And that's sort of the one time I think it is probably acceptable to do a manual garbage collection, because you really, at that point, you really do know more than the garbage collector does about the state of the system. You know it's a perfectly fine time to pause, but as soon as you turn on those sockets and accept user-facing traffic, it becomes a much worse time to pause. But overall, in general, you probably don't want to be calling system GC. That's probably a sign that things have gone awry. So normally, if you are using a 64-bit system, by default, your object pointers, you'll have these 64-bit object headers. So you can, if your heap is small enough, if your heap is, say, 31 gigs or below, the JVM will compress those object pointers for you. So even though you're on a pretty large heap on a 64-bit system, it can use 32-bit ordinary object pointers for you. And this is not on by default. And so if you have a heap that is below 32 gigs, this is probably a good thing to turn on. So another thing to know about is, have we stopped at 4:30? Yeah. OK. Another thing to know about is NUMA. So on modern architecture, not all memory is equally close to every processor. So certain memory is closer to certain processors than it is to other processors. And on some systems, it might be twice as expensive to access certain memory. So the JVM has a use NUMA flag that you can turn on and try to take advantage of some of this memory locality. And if you think about our mark and sweep algorithm, and if you think about the cost of every access as we're walking through that heap being half as much or twice as much, it could really affect the time it takes to do mark and sweep. So this is something to keep in mind, and it's also just generally keep in mind as you're building systems that not all memory is equally cheap to access. And I think this NUMA memory might not only faster access but less bus contention, because there's fewer hops in some systems to get to it. Paging is a big topic. So there are two types of different page faults in a system. This is not solely like give me page 1, page 2. This is systems level paging. Although deep paging, I wouldn't even want to try to tackle. It's a very controversial topic. OS level paging I feel comfortable with. So the two types of page faults, major and minor page faults. Minor happens. It doesn't mean there's an error, even though it sounds like the word fault should be something you should be upset about. It doesn't mean there's an error, necessarily something bad happening. It just means there's some mapping mapping work needs to be done by the OS. But major means that things have probably gone awry if your Solr process is has major page faults. So basically that means you've had pages of your JVM that have been taken out of system RAM and written to disk. Because the system was constrained on resources. And again, if you think about mark and sweep, and you think about every page of memory, and by default on Linux, pages are 4K. If you think about every 4K page of memory going back and forth from disk to memory just to do that marking work, especially if you don't have locality of references, if you have, let's say, a fragmented heap and you're moving all over the place between pages, it could take you a really long time. So you'd never want your Solr process to get paged out to disk. So how do you know whether you're having page faults or not? So here's a little monitoring script where we're basically, you get a lot of useful information right out of PS. And so we're recording every minute. We have cron that runs this thing. We record minor page faults, major page faults, and then we just netcat this over to a Graphite server. And so we have these minute-by-minute counts of major page faults and minor page faults. And they're very useful, and we didn't actually see really any major page faults. So this wasn't, for us, a root cause. And the reason is that we have a lot of RAM on our boxes. Not all of it. We have 96 gigs of RAM on the system, and our indexes are big, but they're not that big. They're 10 gigs, 15 gigs. So all of the not only the JVM heap, but the indexes are kept in the OS's file buffers. So all of those things are very fast to access. And then whatever else is happening on the box, if you have things starting up and running, you want to make sure there's enough RAM for that stuff, and these things that you really care about. And RAM is cheap, so don't be shy. So you don't want, even in a case where you're running low on resources, you really don't want the system sort of aggressively paging things out to disk. And so in Linux, there's something called swappiness. By default, the system is sort of tuned almost for desktop swappiness or medium swappiness, where it will take things out of memory and put them to disk. And on a server, you really don't want this to happen. And so swappiness will make it less. If you set it to 0, it won't make it never happen, but it will make it less likely to happen. If you never want it to happen, and you probably do, there's something called mlock and mlock all, where you can basically lock your RAM. So you start your process up, and you just lock in all your memory pages, and you tell the system never, get something else, not my pages. And so this is actually a technique that's used in a lot of popular JVM-based servers, Cassandra, LinkedIn's Voldemort, Elasticsearch, everything uses this JNA library, which is sort of a nicer way of doing JNI to call out and call mlock all, make the syscall. And I think it's something that can make a good Solr contribution. Probably be nice to have in Solr's main method of starting up in a parameter to say mlock all the memory, and then it never goes away. And then let's say things get really hairy, and you just run out of memory on your machine, and you're on Linux, and you've got the killer. So you run out of memory, and the system is going to find things to try to kill. And let's say Solr is the most important thing on your box, and you want to tell it never kill Solr. So you give the PID of Solr, and you say obviously echo negative 17, and that tells it kill somebody else. So you got to be selfish. So huge pages. So as I said, pages by default are 4K. That seems pretty small when you have a 96 gig heap or a 200 gig heap or just on the box. You've got 96 gigs on the box, and you've got 4K pages. That's a lot of pages for the OS to have in a table and manage. So these days on Linux and newer kernels, there's something called huge pages, where you can configure it. I think almost anything you want, but I think 2 megs seems to be a standard way of bumping it up. And then there's JVM parameters. Use large pages and large page bytes and sites where you could take advantage of these large pages. So the VM has sort of fewer OS level pages to monitor. Then another thing you do is when you start up, you can pre-touch all your memory pages. So instead of having the memory pages be touched as you're using them, as you're allocating memory to them, you can touch them all immediately. And this will really slow down your startup time if you have a big heap, but it will avoid the cost of touching memory later on. So as I said, this talk has been sort of backward-looking. Experiences, problems that we've encountered, bugs that we've created for ourselves, and things we've learned from that. So the next few minutes is going to be kind of speculative and about where, given our experiences, where I think we're headed for our infrastructure. So this might all change, but or we might see you in Dublin in a few months and talk about this stuff very triumphantly. So I think where we're headed, you saw our 31 gig heap. Where I think we want to head to is many small VMs instead of one large VM. Some people call it micro sharding, which I don't like because it sounds too buzzwordy. So imagine you have a 32-core Solr machine, and you send it a very expensive query. It's going to take 5 seconds. And you look at the system under HTOP, and you watch all the cores go. How many cores are operating? 1. It's 1 core. There's no big benefit, concurrency benefit to all those cores. It's going to give you throughput, but it's not going to give you concurrency. Just the way Lucene's algorithms work, it's not like a fork join, embarrassingly parallel problem. It doesn't really work that way. So if you want to parallelize, you've got to just make the index smaller and do the Lucene work in in separate indices and then merge it all together, which creates its own problems, of course, because then you've got let's say 30 different shards. Let's say you have a 32 core, 16 virtual core, 32 physical core, 16 physical core machine, and you split your index in 16. Now we're back to the sharding problem of the slowest shard is going to limit your throughput, which is why we're thinking a lot about backup requests. So there's other benefits that I can see to having very small heaps. So there's a garbage collection talk. It's much easier to garbage collect a small heap than it is a big heap. For the non-Azul collectors, for all the Oracle collectors, big heaps are a problem. There's no magical solution that avoids large pause times. So you can't scale just by adding more RAM. The pauses are still the limiter. And there's things you can experiment with, like CPU affinity. If you maybe assign each micro shard to a particular CPU core, you might get some benefits there. There's optimizations that JVM can do if it knows it's only running on a single core. And certainly you get the benefit of 32-bit pointers. There's certain locking instructions you can get rid of. But then you've got new problems. You've got lots of processes to manage all of a sudden. Instead of just one process per machine, you've got lots of ports. There's more configuration. You've got a multi-tenancy problem. So another thing we're thinking about is putting all of our indexes in RAM. And they're already in RAM in the file buffers. But we want them in RAM in the heap, fully decoded. And if you were in San Francisco a couple of years ago, you might have seen Twitter's Michael Bush talk about these performance benefits they got by having a fully decoded index or reasonably decoded index completely in RAM. And we have a similar problem to theirs in that, or similar opportunity to theirs, in that most of our data is small. And so by default in Lucene, you can index a book. And Tom Burton West, who might be here, he indexes books. He's got 10 million books, and you can put a book in one field. But we've got little tweet-sized titles, and you could express the positions as bytes and save a lot of room. And so that's something we've been working on. I've been working on. Hope to contribute back. There is an example in Solr now, in Lucene now, of a fully in-memory codec called the direct postings format. But for us, it causes there's just simply too many objects that make it to old generation, and then old generation collections become way too expensive. So we want sort of fewer objects, and then the ability to say, this field is very small, so you can limit positions to a byte. You can limit term frequency. There's never going to be more than a byte-sized term frequency. There's never going to be more than a byte-sized position or offset. So that's something we're working on, and then possibly storing those off the heap. Possibly using some of Sun's dangerous, unsafe libraries to access these things off the heap, so that the GC doesn't even have to see them. So we'll see. It's something like I said, this is sort of speculative ideas we're kicking around. And once GC has kicked you around enough, you start to think about moving memory off the heap. We'll also probably try G1 again. Like I said, it crashed on us a couple of times a few years ago, but there's been lots of point releases since then, so we'll probably try it again, and I think it might have more success on smaller heaps. And then we actually did test the Azul C4 collector, but when we tested it, we had some bad memory leaks, and they have much more sophisticated garbage collection algorithms, but I don't think they can fix our memory leaks. Although I have seen recent releases of C4 that claim they have memory leak detection, and if they can heal a bad pointer, maybe they can detect a pointer that's just really old or not rough. I don't know. So we want to try it again. So if you love garbage collection, and who doesn't, I have good news for you. There's plenty to read. The Garbage Collection Handbook is sort of the book on garbage collection, in that there's only one book that I could find on garbage collection, so it's the book on garbage collection. Nobody else wants to write another one. And if you go to the website for the book, it's got a database of 2,500 different GC articles, which you can read at your leisure. And actually, the one thing that I've been sort of interested in for Solr and Lucene is, Solr and Lucene, I was talking about how you have this ref-counted Solr index searcher, and you've got Lucene segments being merged in the background. That is kind of another scenario where I feel like we might know more about the patterns of the heap than the JVM does. I know when a Solr index searcher can be cleaned up, whereas the JVM might not. We have 5 minutes left. OK, so let me finish this section really quick. So that's something I'm interested in. I've actually tried to find some.
There's nobody after you, so if you want to go long and everybody here is happy with it?
People, it's 85 degrees out and sunny, and let's stay talk about garbage collection another hour. Yeah. Java Performance, you should read this. This is, I feel like most people don't know about this book, oddly, but it's a very good coverage, and I feel like there hadn't been a good book about sort of state-of-the-art Java performance for, since 2003 or something. And this one is pretty good. It's by some Oracle guys who kind of know what's going on. And our very own Mark Miller, who spoke right here, right before me, has a great article on Search Hub about all the different collectors and how they work, and more detail than I gave before. It's really good. And his recommendation was similar, to sort of stick with throughput until you find pause times to be unacceptable. Then you can try CMS, but watch the failure modes are kind of nasty. And then Gil Teen from Azul has a very good video and set of slides on understanding garbage collection that's really worth watching, since he is the author of the best GC in the world. I consider him sort of the heavyweight champion of garbage collection, so he's worth listening to. And if anything I've said conflicts with what he says, he's right. I'm not. You should also read Ulrich Repper's What Every Programmer Should Know About Memory. This will give you a really good idea about things like NUMA, things like CPU caches, the cost of memory access, L1 caches, L2 caches, L3 caches. Get to know your system, get to know the proc file system and how to dig into there. This is a great paper. And one sort of trivial but nice thing is this little GitHub project that indexes all, and without looking, who knows how many total JVM options there are? It's 907. I wanted to ask give out a T-shirt to the person that knew that, but there's 907 different JVM options, and this has a nice little search feature. You can actually search for them. It's got a little summary. It does this by actually grepping the source code. Speaking of the source code, you should feel free to clone the Mercurial repository with the OpenJDK, and don't be afraid of it. If you're not sure what a flag does, look in the code. It's actually not as scary as it seems. Like the little bits about how system.identity hash code works, I was always curious and just looked in the code. It's right there. And because not everything you read is true, and you know the stuff that's in the JVM is true. And more esoterically, there's a great Google group called the Mechanical Sympathy Group, which is sort of low-level hardware-software interface, computer architecture, nerding about locking and high-performance Java. I think it's very useful if you're interested in this sort of thing. One of the things I learned very recently, and it really helped us find a performance bottleneck, was that there's a new version of Log4j coming out. It's in beta right now that works around a lot of the really bad locking problems in Log4j 1.x. And we actually went back and tested and turned off our logging and put the system under some load, and it's a bottleneck. So it's a really good group for that sort of thing. And thanks for coming. And let's do more questions. How common is NUMA in commodity servers? That's a good question. I think as of Halum's, I think it seems pretty common. But you can go. I forget exactly what the command is, but you can inspect. I think it's the proc file system, and it will tell you the relative cost for each of the CPUs, how much memory access cost each of what the NUMA cost is between different CPUs. Like what's the distance between two cores? So it'll tell you. Any other questions? Yeah, so we don't have the YourKit agent running. So the question was, what do you have running all the time in production for monitoring? And so the thing that we do have in production all the time is Logster. So this is, oh, you know what? No, not in the JVM. So this is actually just reading the GC log. So it's kind of a hacky way of getting the information, but we just tail the GC log and read it line by line, and that tells us as much as we need to know about.
The GC log was on the production all the time.
Yeah, yep. So the GC logging is on all the time. We don't have the YourKit agent, because the YourKit agent is doing sophisticated things like rewriting your bytecodes to add instrumentation, and that's not totally free. But tailing the log in a separate process is pretty close to free. So we do that all the time. Cool. Thank you.